specific notes on these, okay? So the first part of the video, we're going to talk about a little bit on the periodic table. So where do I find electronegativity on the periodic table and what that means? Okay, and just kind of reminding ourselves what this electronegativity is, okay? So electronegativity is the tendency of an atom to hold onto the electrons in its valence shell. That's what electronegativity is. So think back to the polar bear comic. Polar bears tend to be stronger than penguins, right? From that comic. So polar bears are going to hold on to that ice cream cone a little bit more tightly than, say, the penguins, right? And so when we take that idea and we apply it to the elements, we have things that we call the polar bears. And so the halogens over here, sorry, let me make that a little bit thicker so you can actually see it. The halogens, those tend to be your polar bears. I've talked about that in class. And your metals tend to be more the penguins, okay, not as strong. So over here, these guys, and let's not include hydrogen, but those metals, they tend to be very low electronegative, meaning not as strong at holding on to those valence electrons. And if you take a look at the periodic table that you have available to you on Schoology, it tells you a number for electronegativity for each element. It's the bottom right corner. So if we look at the bottom right corner, say, of lithium, we see it's 1. And then go down to francium, it's 0.7. So it looks like as I go up the periodic table, I increase in electronegativity. Now let's compare the 1 of lithium to fluorine's 4. So it looks like as I go to the right of the periodic table, my electronegativity increases. So if I go up the periodic table, I increase in electronegativity. If I go to the right of the periodic table, I increase in electronegativity. So my strongest element in terms of electronegativity happens to be fluorine. So he's my biggest polar bear. All right, so keep these numbers in mind, bottom right-hand corner in mind, as we move on to the next part of the notes. Dipole is another term that we're going to use in class, and dipole simply means a separation of charge. To have a separation, we look at the electronegativity. Oh boy. Of each element involved in the covalent bond. Now it's important. Covalent is, these are the bonds we've been talking about. You will see me talk a little bit about ionic bonds, but not a whole lot. So we're really focusing on molecules. The strength of the electronegativity determines how hard or how weak a pole there is. So the higher the electronegativity, the harder it will pull on the electrons to keep them close. The elements that have a greater electronegativity will tend to have more pull on the electrons than the elements with smaller electronegativity. So for example, lithium being at a 1 electronegativity and fluorine being at a 4 electronegativity, 4 will tend to hold on to the electrons, whereas lithium might give up an electron. And the bottom of my screen is not working, so we'll just leave it like that. All right, so again, pause the video if you need to copy something down. Now let's use that idea to determine bond polarity. So we want to think tug of war. All right, take a look at this chart here. This chart gives us an idea of the difference in electronegativity, and then whether it is a a covalent or ionic bond. And for covalent, we have nonpolar and polar. Polar would have a dipole, a separation of charge. Nonpolar would not have a separation of charge, okay? So we just want to classify bonds first, okay? Now let's go on to using that chart. I have down below, to determine the bond polarity, I have two different element or bonds that are formed, okay? And we're going to determine whether those bonds are covalent or ionic, and if it's covalent, if it's nonpolar or polar. All right. When we determine bond polarity, the first thing we need to do is find the negativity difference. Okay, that's what END stands for, electronegativity difference. So what I need is, I need to look at the bottom right corner of carbon and the bottom right corner of oxygen to see their electronegativity. Carbon has a 2.5 and oxygen has a 3.5. So to find the difference, I do 3.5 minus 2.5 and I get a 1. This is my electronegative difference. If I look at the chart, which you should copy in your notes, I see that 1 fits in this category right here. So we would say that carbon monoxide is a polar covalent bond. Okay, so they're going to share electrons. Think polar bear and penguin. They're going to share their ice cream cone. Not so much equally, but they're going to share it. Okay. Now let's look at sodium chloride. So we go ahead and find the electronegative difference. Look back at your periodic table. Sodium has a 0.9. And chlorine, which is close to fluorine, has a 3. So we're going to find the difference between 3 and 0.9. So 3 minus 0.9 gives us an electronegative difference of 2.1. When we look at our chart, we see that 2.1 lies in the range of ionic bonds. So we know that sodium chloride is an ionic bond. That's where you have a complete transfer of electrons. All right, so now we're going to take bond polarity and we're going to throw it into a molecule. So how do we determine molecular polarity? Let's talk about molecular polarity first. Molecular polarity is, just like with bonds, we can look at molecules and determine whether they are polar or nonpolar. It is important to note that when you are looking at a molecule, the ones we drew Lewis structures for, we only assign polar or nonpolar since they are covalent, which means they are sharing electrons. If electrons were not shared, then the substance would be an ionic bond or a compound, not a molecule. Okay, so that's important to note. Molecular polarity. First, we want to draw the Lewis dot structure. We've had lots of practice with this, so when I look at H2O, I know that H has 1 valence electron, but there's 2 of them in this particular molecule. And oxygen has 6 for a total of 8 valence electrons. So I put O in the middle. Now, if you remember from our lab, we know that H2O is going to be bent, and it's going to have 2 lone pairs. Okay. Now, because oxygen has a higher electronegativity it's going to pull electrons towards in that direction. And remember, we're talking bond polarity, and hydrogen is electrons are going to be pulled in that direction. And if you see how, I'm going to move this guy over a little bit. So we have oxygen pulling harder, not sharing equally, right? Think of the ice cream cone. That oxygen is a polar bear, pulling harder in an upward direction. So this total, right, is going to end up being pulled upward, giving what we call a dipole effect here. This side will be more positive, so we say partial positive charge. And this side will be a partial negative charge. This is a polar molecule because it's pulling, oxygen's pulling harder in one direction, up and out, but more so up, okay? It's an unequal pull on the electrons, okay? So it creates this dipole effect. Let's look at carbon tetrahydride. First, draw the Lewis dot structure for carbon tetrahydride. So carbon has 6 valence electrons, hydrogen has 1, but there's 4 of them. So we have 10 total valence electrons. Carbon goes in the middle, so we have a hydrogen, 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 hydrogen. And then we see that we have carbon is a higher electronegativity, so it's going to pull that hydrogen down. It's going to pull this hydrogen up, and those are going to cancel each other. Okay? Same thing here. Carbon's going to pull the electrons closer to itself, to the right from that hydrogen, to the left from that hydrogen. So notice that all of these pulls on carbon, on the electrons, are going to end up canceling out. When they cancel out, those directions, that pull, we have a non-polar covalent bond, or molecule. Let's look at a few more examples, okay? Carbon dioxide. So we draw out the carbon dioxide structure. Carbon has 4 valence electrons. Oxygen has 6, so we have a total of 16 valence electrons. Carbon goes in the middle, oxygen to the sides. We fill up our valence shell, but carbon's not happy, so we take 2 electrons from oxygen there and 2 from oxygen here. So we have what we call a linear molecule. And then if we take a look at the bonds, oxygen has a higher electronegativity than carbon. So oxygen is going to pull the electrons closer to it that way and this way. And take a look, those are opposite but equal pulls. So they're going to cancel each other out. And that gives you a non-polar molecule. So carbon dioxide is non-polar. Non-polar. And then the last example I have for you is CH2O. So